which looks like this. Are you guys familiar with that? This.
I've seen it before.
The horizontal lines moving towards, so wedged, and vertical on top and bottom will be away, so dashed. This like that. And then for Newman, we start with the Newman projection. Just let it in. So you kind of have to look at it from the side. So imagine your eye is like here looking at it, right? So these two groups are towards you, right, closest to you, and then these two are away. So what I do is first I start off with just drawing like this, and then the groups that are pointing upwards and downwards, A and F, I put there, so A and F, right? And then each of these corners will have a dash and a wedge. And also I like to draw the dashes in between, because that'll help when we convert to Fisher. But then looking here, A and B are towards us, right? So they're going to be on the wedges. And then you pick which wedge depending on which carbon that it's attached to. So B will be with A, and E will be with F. And then D and C are away from where I drew the eye. So D will be with F here on the dash, and C will be with A here. Does that make sense?
Can you re-explain that?
Yeah. So when you're given a Newman projection, just always start by drawing like an eye there, so that you know like which groups are closest to you and which are away from you. And then when I'm converting it to this like long line structure, I start by drawing like this, right? And then these two will be the one that's pointing straight up and straight down. So A and F. And then each of the corners,
So the top one will always be the one that's pointing towards you?
the one that's straight upwards, yeah. And then each of these will have a dash and a wedge. And again, I like putting the dash in between. So like not here, not like that, or the other way, because it'll just help when we look at it from this view. And then you see that E and B are closer to the eye, right, that we drew. So towards is always going to be wedged. And away is going to be on the dashes. And D and C are away, right, furthest from the eye. So then we have two wedges. B and E are going to go on them. And then depending on which carbon it's on, that's how you know which wedge to put it on. And then the same for D and C. Okay. And then
Why is DNC away?
because that's why you start off with which side are you looking at the projection from, right? So I always typically go from this side. I would stick with one so that you don't get confused.
Okay.
And then since we're looking at it here, this is an eye by the way.
Okay.
Since we're looking at it here, E and B are closer to this side, and B and C are away.
Mm.
Yeah. Yeah.
On the exam, we can put the I on like the left or right, we just have to be consistent with.
Consistent.
Okay.
Yeah. And while you're practicing, I would also just choose one side. And then this can easily be turned into Fisher. You don't even have to dry it out, but so obviously the ones on the dashes are on top and bottom, right? So C and D. And two wedges for each, but knowing which side it goes on, I wrote down, the one that's down is gonna go on the right, and the one that's up on the left. So in this case, B is down, so it's gonna go on the right. A is up, so put that on the left. And then E is up, so left. And D is, oh no, F, sorry. F is down, so right. And then, yeah, I should put that there. Just double check. Yeah, one second. I think that should be right, but yeah. And then that can also be written as like that. So as I was saying, like when I write it this way, if we're given a Newman, I like to put the dash in between. But sometimes you're just given this, and so don't let it confuse you if the dash is like not here instead of here. Because when you look at it this way, it's still going to be on top. But let's say you were given
I have a
this
question.
instead. Yeah.
Do we have to convert it to Fisher?
Not necessarily.
Because I think when he was doing Newman, he just like kind of visualized the rotation, if that makes sense, without having to draw the Fisher projection.
This is what helped me because I know if I'm just working with the Newman, like it's a lot of like
It's hard for me,
imagining. Yeah.
Okay.
So I had to like draw it out.
So
Yeah.
this is like I guess what you're looking at to do it to get to the same I guess answer.
Yeah.
Yeah.
If you find this helpful, then I would recommend it.
Okay. Thank you.
But you could also work with like I know.
No, I've been trying to do it.
Yeah.
Yeah.
It was really confusing for me too.
Thank you.
Sorry, how did you know C was on top in the Fisher?
C was on top.
In Fisher?
Oh,
From Newman to Fisher.
since we like just started from left to right, I'm kind of just rotating it.
Okay, so everything that's in the back, like C and T, they go at the top and bottom.
Oh, you mean like, oh yeah, so the ones on the dash are always gonna be top and bottom. So for Fisher,
Oh, geez.
The vertical lines?
Sorry,
Yeah,
got it.
like that, yeah. So if you're given this instead, again, C and D go on top because they're on the dashes. And then the ones that are down will be on the right. I feel like I got this direction wrong. I'm just gonna double check when we do practice. And then finally, for cyclohexanes, you might be given a cyclohexane. Just know that upwards will be towards and down will be away. So if a group is axial upwards, that's going to be towards. If it's equatorial downwards, still away. And the same goes for if it's equatorial upwards, it's towards. Axial downwards, away. That's all the like converting from different directions.
Can you clarify?
Why did you flip, sorry, why did you flip up the D and E in the,
D and E?
yeah,
Where?
the D was in the wedge,
From which one? This?
yeah, that one,
This one and,
from,
That one?
yeah,
That's in your
oh,
part.
I was showing you if you got this instead of this.
oh, okay.
So this would then become this.
Oh,
yeah.
alright.
Can you clarify that part again where we're going from the skeleton of the movement to the fissure? So we said that the down would be on the left side and then everything on up would be on the right side? Like from A,
Here to here.
I don't know, the second part?
Here to
Yeah,
here.
from there to there.
Yeah. So we know that C and D are going to be top and bottom, so deciding whether like A and B, because they're both going to be on wedges,
Mhm.
but deciding which side they go on. So since A is up, I put it on the left, and B is down, so I put it on the right, and then I keep that consistent with this one. E is up, so I put it on the left, and F is down, so I put it on the right.
So you get to choose which side of the fissure goes because you're like assigning as long as you're consistent.
Exactly. That's like a common theme with this. Like as long as you're consistent, it should be right. Yeah. Erase this. Once we get assignments of R and S, we know that it's the same if it's, let's say one compound, they have each has two chiral centers. For the first one, it's RR, and what would be the same for the other one? RR, right? And then SS versus SS, those are gonna be the same. And the enantiomers will be, the opposite. So there's a couple, there's 4 combinations, so RRSS, SS, RR, RS, SR, SR, RS. And then for diastereomers, one is gonna be different and one's gonna be the same. So RR, RS, RR, SR, SS, SR, SS, RS. And then you can just like flip these. So what should we start off by doing? Counting the number of atoms, right? So these each have 6 carbons. Does it look like it has all of the same atoms?
Yeah.
It does.
Yeah. So they're not different. And then next was arrangement, right? Are they arranged the same?
Everything is the same except for
Except for the what?
the double bond.
The double one, right? Yeah. So here it's like in proximity to this carbon, it's 1, 2 away. And here it's 1 away, right? So different places. So these are concentrations.
Where can we go and read these definitions?
Read the difference.
Yeah, I wasn't here yesterday, so I don't know what that constitution means.
I have
It's gonna be in
information
the
on the
slides.
but I'm sure the textbook probably has all the definitions.
Constitution is the,
Think
different
one-
bond connectivity.
Yeah.
Oh, okay.
She was still copying. It's okay. I'll see it just there in the slides.
Yeah. That one. Are they different? Like any different atoms?
We swap, we're literally going and swap places.
Yeah, they swap places, right? But
They're different.
no,
Are
they're not different
they're
though,
not different.
because they still have all of the same
Yeah.
atoms.
Everything is the same. If you would just grab this molecule and flip it like this,
Yeah.
it's the exact same thing.
And even connectivity, right? Like it's kind of just like rearranged differently.
Wait, is it? I'm sorry.
Not
How many
rearranged, but like that was
how many
wrong.
carbons are in the second one?
Sorry, this is wonky. I'm not an artist. Yeah.
If the atoms are placed differently, though,
No.
so would it be would it be constitutional?
No.
It would-
I think it's.
They are the exact same atom, like molecule.
That's just a mirror image.
Yeah, it's a mirror image. Like
Yeah.
it only means front and back. It's like this, right? This would be HO, this would be CL. If you just do this, now HO is in the back, so it looks like
So
that.
it's the same.
It's the exact same.
So what would have made it
So all this
constitutional?
indicates is that in here, the OH is like sticking out of the plane, and the CL is like going into it. And then here it's the opposite.
So you just flipped it, like you said.
Same.
Yeah, they kind of just like rotated. Yeah.
What would have made it constitutional?
Constitutional would have been like if this was here.
Okay, got it.
Yeah.
Thank you. Yeah, that helps.
Constitutional means that everything is the same, but just it's rearranged differently.
Yeah.
Okay.
And
And what is this called? Same?
yeah, so it's the same because we see a plane of symmetry, right?
No, I know it's the same, but what is it called? Like, what's the answer in the
It's
exam?
really just the same
Okay.
concept on the example.
Oh, it's literally the word same?
Same
Oh, okay. Oh, same.
So-
Okay.
Not only do we see a plane of symmetry, what else do we notice? So like, you guys saw, OH was wedged here, now it's, dash, so like, there's one dash, one wedge, right?
Right.
Trans.
Yeah, so they're trans, and what does that mean?
So they can't be biased.
Yeah. Not diastereomers.
Is it trans?
Yeah, one is up, one is
One
down.
up, one down, one up, one down.
But that doesn't, just because you rotated a molecule doesn't change the place that it is. Like the way it's arranged. It's just a different perspective. So if I look at a hydrogen and if I look at an H2O and I walk 2 feet in a circular motion,
No, they're
Doesn't-
each trans. Like this one's trans and this one's.
yeah, they're not trans from each other.
Yeah.
Okay, okay, never mind.
And the plane of symmetry means it can't be exactly. So the only thing we're left with is same. They're the same.
Look, that's why I love computer.
I didn't get anything to
Just to confirm, a diastereomer has one cis and one trans, and an enantiomer never has a plane of symmetry. Okay, thank you.
What about this one? Are they different compounds?
They're both hexo.
Not right.
That
That
one's-
still has 6 carbons.
That has 6 carbons. This one's on 1. That one's on 1, 2, 3, 1, 2, 3, 4. What the fuck?
They're each
1,
like
2, 3, 4.
1, 2, 3 carbons away from each other. Right.
Oh, I thought it was because that one looked 1, 2, 3, 4, 5, 6. So it's 1, 2, 1, 2.
If you
3,
kind of
4.
imagine
They're both-
these
yeah.
corners coming out.
Yeah, they're both exactly the same, right? Yep. No, are they?
Well, not yet.
No, no, they're not, because it's gonna be, OH is gonna be up, meaning solid, and CL is meaning down, it's gonna be spotted.
But what did we say about cyclohexanes? If it's pointing up
It's
towards, and if it's down,
It's towards.
Yeah, so
wait,
it's,
right, and the same
yeah,
area.
it's the exact same thing, but flipped again, right? Is it? Well, we
yeah.
had like a week before, yeah.
First, we see that they're both trans. So, not diastereomers. Is there a plane of symmetry?
No.
Yeah.
Yeah. Come on. And then this is kind of hard. You know, but yeah, there is a plane of symmetry. So they're not enantiomers. And therefore, the same. Yeah.
So for the example, you usually straight so about kind of like the plane of symmetry, or did you assign about the RS? Because even if you knew it wasn't something, you still assigned it.
So
Like for this, he probably would have assigned.
if like none of these were the case, if like I didn't know whether it was cis or trans or there wasn't a plane of symmetry, that's when I start doing the R and S. But if you can like figure this out beforehand, then it saves you time. Yeah.
That's better.
Are they different compounds
No.
arranged differently? No.
Well, the double bond, the
But the
double
double
bond
bond
is.
it's still the same
It's-
place, right? Away from like the chlorine and the bromine. So that's fine. But we do notice this chlorine's like downwards, this one's upwards, right? So
It's also different amount of carbons, right?
this one's down and up,
This one's trans and the other one is cis.
down and down.
Says.
So this there is DS.
Yeah. So since one is trans, one is cis, automatically diastereomers. What was that?
I don't know, I can't say. Diaster?
Diastereomers?
Diastereomers. I'm just thinking of disaster mers.
Question, if VR was dash, that would be considered, pointing up, right?
No, I don't think so. I think
I thought solid was up or towards us. Dash is behind us.
yeah.
So then wouldn't VR on the left side technically be an up? Or do we avoid that for now? And then we just look at it the way that it's positioned?
I don't know if in this case we
Or how would we know?
look
See
at
it?
whether it's wedged or dashed, but rather like the way that it's put in.
Instead,
Wedge is towards and dash is away.
Yeah, that
Yeah.
also helps when we're doing this part, the RNS.
So what would apply in this case because.
Yeah, in this case, we're just seeing which ways it pointed. Yeah.
Don't. Oh, I see what you did there. Shows the windows that. Just notes from the slides. VR is VR in the seal.
But wait, if we said that it was styles, whatever, however you say that, don't we have to find if it's RR, SS, or afterwards?
I just started off by showing ways you can know that it's diastereomers without having to do that.
Ah, okay.
So if one is cis, one is trans, you know automatically.
So mutual COH is forward. What?
So are they different?
Yes,
Why?
because CH3 is on the end side, H is at the bottom side. If they were the same, CH3 and would be across from COOH. The carboxylic acid would be across from CH3.
What do you mean?
So you see how you have
It's
a
arranged?
yeah, you see how you have CH3 and H at the two ends of the second molecule?
So this is the back carbon, right? And this is the front carbon.
Right,
So this carbon has CH3, OH, and Br,
right.
and the one behind it has hydrogen, chlorine, and carboxylic acid. Does that stay this consistent there? Like if this is the front carbon and this is the back carbon?
Shouldn't the carboxylic acid be switched with the hydrogen?
Yeah.
Because, you know, if the I is on the right, then hydrogen is sticking forward, right?
Not necessarily. So the way that I drew, like if I was given this, that's the way I would draw it, because it's gonna help me like when I convert it to Fisher.
That's not the way.
But this was
everybody-
given. This is just the way that they gave it. Yeah.
Okay. Yeah, it's the same for both.
Yeah,
It's the
They're not different compounds, and they're attached to the same carbon. Like the groupings are the same.
I thought you said that the ends of the second molecule would have to reflect the across from each other for the left. So CH3 must be across from this carboxylic acid, but in the second one it's across from H.
This isn't like bond line. It's not Fisher yet, but we can convert this into Fisher. I'll actually redraw. So when we're
What?
given these two, like let's say I'm given the Newman, right?
Yeah.
I say that I like to draw it. Like that, and then I can CH3 here, COOH. And, let's say my eyes here. The ones that are towards me are H and BR, right? So that's gonna be on the wedges. BR's with CH3, OH, so here, and hydrogen would be here. And then Cl and OH are away. So
How do you know which one to put next to BR? And that specific one?
so BR here is connected to this carbon, right?
Yeah.
Which has the CH3 and OH. So I'm gonna keep that
Ah.
consistent, yeah. And then OH.
Right.
And then I kind of just already imagine, since the dashes are in between, right? If this kind of already looks like Fisher, right? All it's missing is the legs.
Right.
And then this is one chirocarbon. And this is another. It's ranked by the atomic numbers. So for this one, it has a hydrogen. If there is a hydrogen, that's gonna be 4, the smallest. And then there's chlorine, there's a carboxylic acid, and this carbon that's attached to a bromine, OH and CH3. So chlorine would be 1, it has an atomic number of 17. And then between carbon with an oxygen versus carbon with the bromine, which one would be second? Bromine's 35, oxygen's 8.
Yes, sir.
Bromine, right? So this will be 2, and this will be 3. And then direction from 1 to 2 to 3 is like that, right? So we're going counterclockwise. So
But,
we can give it S.
sorry, to get to this, you have to now count the weights of the carbons that are found within the molecule?
The atomic numbers. So we're ranking by atomic number on your periodic table.
So every single one.
Yeah.
So then also
So the
the,
4 different groups, right? We identified 2 chiral carbons.
we identify to what?
2 chiral carbons, so carbons with 4 different groups. Does that make sense? So this carbon has 1, 2, 3, and then this.
What's a chirocarbon?
So we went over that the first part of class, but chiral carbon just means carbon with 4
Like-
different groups.
Like a chimera?
A what?
That's what they give sometimes to things that are multiple, the naming. Chirocarbon.
Yeah.
So that carbon in there would have what? It would have, the one in the back would be CH.
This one?
The,
Or this one?
Sure, either of them.
So we're starting with this one. This one has a hydrogen, a chlorine, a carboxylic acid, and then this entire group.
Oh, okay.
So there are 4 different groups. Does that make sense?
Yeah.
Yeah, it does. And,
Are you doing your question?
oh, no, I just wanted to figure it out. But then my question is now, how are you ranking the numbers then?
Atomic number.
Right, like how? CL being one of
Yeah.
them?
Cl's 1, hydrogen's 1, and then we're choosing between, so both of these are carbons, right? It starts with carbon, this one starts with the carbon, and this one starts with the carbon. So then we go to the next one. So carbon with an oxygen versus carbon that has a Br.
That was my question. So why is it, the carbon's also attached to CH3 to the like on the back part.
Yeah.
So why BR?
Yeah.
Well, I didn't go in order, but this carbon does have a Br. It has an OH. It has a CH3.
Okay. And
So if it has an atom that has a higher atomic number than any of these, then it's automatically going to be higher priority.
Wouldn't the BR be heaviest? So we start with that one as 1?
No, because to this carbon, this is directly attached to the chlorine, versus this is a carbon with the bromine.
Why are you starting with that carbon on the right?
The 2 chiral centers.
Right, why did you start with the left chiral
I
center?
could have, if that's after.
after the first one, you need to second. You can start with either chirocentres, but she's starting with the first one.
Why are you doing 2 chiral centers multiple times?
It's 2 to get the RS configuration. If there's 3 chirocentres, you're gonna do 3 times.
Yeah.
But I think he said he's not gonna do it.
Yeah, he's only going to give 2 at the
Yeah,
end.
What are these RS mean?
The
We'll get to it.
Oh.
Like, right? Because it's
Yeah.
counterclockwise from 1 to 2 to 3. But what was the caveat? If the hydrogen, the fourth group, is pointing towards us, it's on a wedge, we flip it, right? So this is gonna turn into auto.
What the heck? Okay.
And then this one, Br is gonna be 1, right? And then oxygen, and then we're choosing between carbon with 3 hydrogens, carbon with chlorine and all of that, right? So 3, 4. In this case, the methylation 4.
Wait, I got a question again. What was the logic again behind the switch the S by R?
The switch. Oh yeah, okay. So we went from 1 to 2 to 3,
Yeah.
and that's counterclockwise and it's S, right?
Yes.
But always make sure that when the fourth group is pointing towards us or it's on a wedge, like this, then you flip it. It's the opposite. Yeah.
And what was the priority moving for the second character, for the second parasite?
Br's first, oxygen is next, and then the carbon with chlorine versus carbon with just hydrogens.
Thank you.
I don't understand why a C attached to the Br is in any way more atomically heavy than a C attached to a C, Cl, and H, and a COOH.
So, for priority, the carbon being directly attached to a bromine is going to be higher priority than it being attached to a carbon attached to different groups.
So then by
we
that
first-
standard,
we
we,
start off with like comparing bromine to oxygen to carbon. And then between these two carbons, you go to the next one.
so, okay, so it's the next level. Okay, so then it only honestly matters the first atom attached to that carbon that you're talking about. So
Yeah.
in that case, it would be carbon with bromine, then carbon with oxygen, and carbon with carbon. And if you're attached with something else, oh, I see what I mean. So CH3 would be attached to the C first, then